Alright, so let's start the lecture. So in this lecture we'll be discussing hypothesis testing, specifically focusing on a single population variance and the ratio of two population variances. So let me start with a single population variance. So what do we mean by when we say single population variance here? So what did we test until now? We tested means, we tested the difference between means, we tested proportions, and we tested the difference between two population proportions. So the next topic that we're going to talk about is how do you test whether the population and the sample has the same variance. So do remember that when we take a sample, so let's say when we take a population, so the population, we take a small chunk of that population. So let's say from this particular population, we take a small chunk of this population as a sample. So we only take a small chunk of it. So which basically means here that when we take this small chunk, what we are trying to understand is the fact that as we take this small chunk out, is the sample having the same variance as that of the population? Now the problem with this is that remember that when we discussed in sampling distribution, we said that the variance of a sample is gonna be divided by n times that of the population. Now this is not what we are talking about when we talk about a sample being taken out of a population. What we are checking here is trying to understand whether the sample is from a particular population or not. So I have a sample here, let's call it something, let's say A, and is this sample really from this population or some other population? So how do we know and how do we test this? The only way to test this is to conduct a hypothesis testing. So the hypothesis testing basically states for a single population variance is that we have sigma square, which is the population variance, which is equal to sigma naught square, the testing variance. And the alternative hypothesis is going to be sigma square not equal to sigma naught square. Now the sigma naught square here represents the population variance that represents the sample. So the population variance representing the sample. So the best way to understand this is, let me give you a small understanding example of this. So let's say I have one population right here. So this population has a variance of sigma square, and I have another population here. Now this population has a variance sigma naught square. What we are testing in hypothesis testing here is that rather than comparing a sample variance with a population variance, what we are saying basically is that I have a sample variance right here. So I have a sample variance right here. So we know that the sample variance is S square. We are saying that this sample variance S square belongs to a population of variance sigma naught square. And one thing we want to know is that is sigma square and sigma naught square the variance of the same population. So one way of thinking about this is to think about it like this is one distribution and this is another distribution. So we have two different distributions of different populations with the main variable or the measure sigma square and sigma naught square. What we are saying is that are the variances same so that the populations are also the same. So we're basically trying to understand whether S square comes from sigma square, sigma naught square, and if this sigma naught square is the same as that of the population variance that we are testing. So we have population 1 and population 2. So population 1 is the one that we are testing. Population 2 is the one where we have a small sample of it with S square. We want to know whether these two populations are the same or they are different. So this is the basic sense of population variance. So this is one of the reasons why we use chi-square distribution as a measure or a test, or the chi-square test, best way to say this, to compare the population variance. Or let's find another way of saying this is to whether to find the sample is from the population variance. So this is basically the idea here. Now, chi-square distribution mainly is used so that we know that sigma square generally only has a values greater than or equal to 0. So which means that most of the values that you get of variance are always positive. Now, using a normal distribution is exactly the same as chi-square distribution. The reason for that is because chi-square is basically the cumulative normal distribution. So it basically says the cumulative normal distribution. So cumulative meaning that it adds the values for every subsequent value. For example, if you take sigma 1 square, it basically represents sigma naught square plus sigma 1 square. So whenever you take these values, you're basically saying that the one where this next value is the sum of the values of the ones that are before the other two. Now let's get into hypothesis testing of a population variance. So what are the steps here? So we know that we have the null hypothesis, and an alternate hypothesis. Which is HA. The null hypothesis basically says that both variances are the same, and the alternative hypothesis basically says that no, both are not the same, they are different. So how do we test this? So we use a chi-square test. So in chi-square test, we calculate the value of chi-square. So chi-square value is calculated as n minus 1 times s square by sigma square. So s square representing the sample variance and sigma square representing the population variance. So remember these two, that s square represents the sample variance and sigma square represents the population variance. So whenever this h naught, so this chi-square is represented by two different values. One is what we call df and the alpha value. So df here represents the degrees of freedom, so which is basically the number of values in a sample, the size of the sample minus 1. So remember this when we want to calculate the value from the table. So we do have a chi-square distribution table that we generally use to calculate these values. So let's take a simple example of this problem and let's understand the question from the problem itself. So what do we have here? So the purpose of study by Wilkins was to measure the effectiveness of recombinant human growth hormone, or HGH, on children with a total body surface area burns greater than 40%. In this study, we have 16 subjects who received daily injections of at-home RHGH. At baseline, the researchers wanted to know the current levels of insulin-like growth factor, IGF-1, prior to the administration of RHGH. So the sample variance of IGF-1 levels in nanograms per ml was 670.81. We wish to know if we may conclude from these data that the population variance is not 600. So again, what is given basically here? We have H naught which basically says that sigma square is equal to 600, which is the opposite of what they're asking us to do. So HA basically says that H sigma square is not equal to 600. Now, how do we calculate the test statistic? So the test statistic here is to calculate the value of sigma square. So here they have 16 subjects. So the n value is 16. And they also had the sample value for the sample. So that is going to be 670.81. And they also gave us the sigma square value, which is 600. So chi-square is n minus 1 times s square by sigma square. So n minus 1 is 16 minus 1 times 670.81 divided by 600. So this value, when you calculate, you get a value of 16.77. Now chi-square, this is the calculated value. So this is the calculated value. So let's put it separately. And this one, the next one, is to find the value of the table, which is chi-square of df comma alpha. So the chi-square value. So remember that this is a two-tailed test. So whenever you see chi-square values, so these are taken to be, so these values generally have to be taken on two sides. So chi-square also has a lower bound and an upper bound value. So we have to take two values here for df. So we know that df is n minus 1, which is 16 minus 1, which is 15. So 15 comma 0.05. So we also need the upper bound value, so which can be written as chi-square df comma 1 minus alpha. So 0.9, sorry, 0. Alpha by 2, 1 minus alpha by 2. So 0.025 and 0.975. So these values are going to be chi-square of 15, 0.025 and chi-square of 15, 0.975. So the values that we have here are going to be 6.262 and 27.488. So let me show you what a chi-square distribution generally would look like. So a chi-square distribution looks somewhat like a right skewed distribution. So this is what a chi-square distribution would look like. So you have one value right here, which is 6.262, and the other value right here, 27.488. So notice that we have two rejection regions here. So we have one on the left and the other one on the right. So the value that we got here in the calculated value, 16.77, is somewhere in here. So this is the accept H0 region. So this region and this region here represents the reject H0 region. So because this chi-square value that we got lies between the two values that we have in the distribution, so we have to accept H0. So we accept H0. So the H0 basically says that sigma square is equal to 600. So what we are saying is that they asked us to know if we may conclude from these data, the population variance is not 600. So we cannot conclude from the data that the population variance is not 600. So this is basically saying that we can conclude from the data that the population variance is 600. So this the upper one is basically a fancier way of saying the down one. So this is how we solve the problem here. So remember that our chi-square distribution, we have to calculate two values when you have a two-way test. The reason why it's a two-way test is because it's a not equal to alternative hypothesis. Now there is a chances that it might be on the other side where we have a one-way test. So if you have a one-way test, what would be the alternative hypotheses? So the alternative hypothesis for a one-way test would be sigma square is equal to sigma naught square. So if it's a left one-tail test, it's going to be sigma square less than sigma naught square. And if it's a right one-tail test, it's going to be sigma square greater than sigma naught square. So this is the left one-tail test, and this is the right one-tail test. So it's easy to figure out this kind of a problem just by looking at the question. So when you look at the question, you have an idea that, okay, this is this a left one-tail test or the right one-tail test, because they generally ask whether it's greater than the value that they have given or less than the value that they have given. So this is how we solve this problem. So pause the video right here. I've given you a couple of problems. So try to solve these problems using the example that we just solved. All right, let me move on to the next topic, which is going to be hypothesis testing of the ratio of two population variances. Now, so we come to the concept of hypothesis testing of the ratio of two population variances. So how do we consider two population variances right here? So whenever you look at two population variances, the one way to think about this is to think about comparing the same concept as the comparing means of two samples. So the same process applies here as well. So we have two populations. So we have one population here, and you have the other population right here. So this has a variance sigma 1 square and sigma 2 square. So the null hypothesis basically says that the population variances are the same, and the alternative hypothesis basically says that they are not the same. So this is basically the concept of the ratio of two population variances. So the reason why we call it the ratio of two population variances is the test involved. So the test involved is called as an F-test. So F-tests are basically the expanded version of a chi-square test, where rather than comparing the variance to the population, we are comparing two variances, which are distinct from one another. So when you see an F-test, you get two different degrees of freedom, representing the fact that it has two different populations. So we have two different populations. We are trying to find out through F-test whether these two are different. So for this, we also use a term called as a variance ratio. So the variance ratio is generally written as S1 square by sigma 1 square over S2 square by sigma 2 square. So because variance ratio is generally collected in such a way that we have two samples, so when we compare the two samples, that would be more than enough to judge whether this value can be the ratio that we need or not. So let's take a simple way of looking at this, is that because when we compare two sample variances, we are automatically considering whether the sample itself comes from the population. So the assumption is that the populations are the same. So we can generally consider the variance ratio to be the sample itself. The reason why we don't use sigma 1 square and sigma 2 square is because these two values are generally not available. So the general assumption is that both of them are the same, and we are just comparing the sample variances. So we condense the formula for variance ratio to that of S1 square by S2 square. So let's take a simple example of this. So one way of thinking about F test is to look at the variance ratio itself. So when we want to calculate the F value or the F statistic itself is the ratio of the sample variances. So again, the same rule applies here as that of the original problem that we dealt with in terms of the single population variance. So we have a statistical value right here. So either we can reject it or we can say that both of them are not the same. So simple way of looking at this is that we have H naught, which basically says that sigma 1 square is less than or equal to sigma 2 square, and HA, which basically says that sigma 1 square is greater than sigma 2 square. Again, this can be different in different problems. So sigma 1 square can be less than sigma 2 square and sigma 1 square equal to sigma 2 square. And the alternative hypothesis can also be sigma 1 square is not equal to sigma 2 square. So it depends on the problem given and depends on the value that is taken. So let's take a simple problem and try to understand this process. So what do we have here? So Borden et al. Compared meniscal repair techniques using cadaveric knee experiments. So one of the variables of interest was the load at failure for knees fixed with the fast T fix technique and the vertical suture method. So each technique was applied to 6 specimens. The standard deviation of the fast fix method was 30.62 and the standard deviation of the vertical suture method was 11.37. Can we conclude that in general the variance of failure is higher for the fast fix technique than that of the vertical suture technique? So the alternative hypothesis that is asked in the problem basically asks whether sigma 1 square is greater than sigma 2 square. So the null hypothesis can be sigma 1 square is equal to sigma 2 square. So it can be equal to or it can be less than, but remember that this is the reason why the alternative hypothesis has sigma squares and the F value does not have sigma squares. So to avoid having any issues with that, we generally use the term less than or equal to for H naught. The reason is because it does not specifically say the opposite in the opposite can be two things here in the null hypothesis. It can be equal to or it can be less than. So let's take the example. So they have given us S1 and S2. So S1 is 30.62 and S2 is 11.37. So N1 is 6 and N2 is also 6. So remember that was applied to 6 specimens. So each technique was applied to 6 specimens. So N1 and N2 we have the values, and the S1 and S2 we have the values. So let's take the F calculated, which is going to be S1 square by S2 square. So that is going to be 30.62 square divided by 11.37 square. So the value is going to be 7.25. So this is the calculated value of F, so which is 7.25. Now when we calculate when you want to calculate the F table value, so you need 3 things. So we need df1, df2 and alpha. Remember that this is a one-tailed test, so we don't need 2 sides of the distribution. So F distribution looks similar to that of the chi-square distribution. So it looks more of like a right skewed distribution. So we have the values F. df1 is n1 minus 1, df2 is n2 minus 1. So it's going to be 6 minus 1 and 6 minus 1 is equal to 5 and is equal to 5. So we have 5, 5, 0.05. So when you take the F table values for this, so that value generally is going to be 5.05. So this is the value for the F table value, 5.05. So remember that this is a one-tail test, so anything to the right of it has to be the rejection region. So this is the reject H0 region, and this is the accept H0 region. So the value that we got is 7.25, which is somewhere here. So which means that this is in the reject H0 region. So we can reject H0 and basically say the alternative hypothesis, which is sigma 1 square is greater than sigma 2 square, is true. So we can conclude that the variance of the failure is higher for the fast fix technique than that of the vertical suture method. So this is how you can solve these problems. Now I've given you a couple more problems of the same method. So pause the video right here and try to solve these problems.